Hello everybody and welcome back to another video by Funlearn Tutorials. In today's video we will be talking about the Lagrangian method of optimization. Note that this Lagrangian method of optimization is used when we are talking about constraint optimization. So we will be essentially talking about constraint optimization in today's video. Now why do we first we need to understand why we need to look at the Lagrangian method and why can we not simply use the method that we usually use. So if we are talking about constraint optimization, suppose we have to maximize a function, say capital Fxy. So this is the function that we need to maximize or minimize. So maximization or minimization can be combinedly called optimization in general. So suppose we have to optimize the function capital Fxy, that is it's a function of both x and y. So this is a double variable function. It's not a single variable or a univariable, it's a multivariable function. And suppose we have a constraint, so we have suppose small fxy, or you can take it as gxy as well, small fxy equal to 0. And when we want to use this constraint optimization, when we want to use this constraint in our optimization, what we usually do is we insert this constraint into our function. So this is in the implicit function. Suppose we have the function, the constraint as x plus y minus 1 equal to 0. Suppose we have this constraint and we need to implement this constraint. Let me just thicken the, So suppose we have this constraint to be followed when we optimize our objective function capital Fxy. Under normal circumstances, suppose we have to maximize the function x square plus y square. Suppose this is what we need to maximize. What we usually do is we say suppose take x equal to 1 minus y, and then we use this x in place of x here. So we essentially maximize the function 1 minus y whole square plus y square. That is what we usually do. This is not Lagrangian optimization. This is simply the general optimization principle that we follow. But in certain cases, if the functions are a bit too difficult to handle when we are transforming the constraint into the objective function, this method might become a little cumbersome. In that case, it's sometimes helpful if we know the Lagrangian method. So now what we are going to do is we are going to do a particular sum based on the Lagrangian method, because mathematics, it's not that easy to understand through illustration, and I particularly feel that examples will do just fine to understand the procedure. So based on the previous notations that we followed, I'm going to take the objective function as capital Fxy and I'm going to take the constraint as small fxy. So let me just write down the sum that we'll be doing right now. So let's suppose I want to maximize, or the optimization exercise remains the same, the procedure remains the same whether we maximize or minimize. We can also call it an optimization exercise hence. Suppose we want this optimization exercise to be done on the objective function x plus 2y. Let me take an easy sum. So this is the objective function. This is what we need to optimize, or that is maximize or minimize. And the constraint. So the constraint, so this is subject to, ST stands for subject to. The constraint is small fxy. So the constraint is small fxy, and the constraint here that I'll be using is xy. So the constraint is xy plus y square minus 1, and this is equal to 0. So this is xy plus y square minus 1 equal to 0. And this is essentially in the implicit form. The constraint is in the implicit form. If we were to follow the previous method, what we would have to do is we would have to convert this constraint and put it somewhere over here, which would imply that it would be difficult to solve for y. So what we could have done is we could have solved for x. X would have been equal to 1 minus y square by y, something of this sort, and we would have to replace x over here and then we would have to solve for it. That would become quite cumbersome, so we are not going to use this procedure. We are going to try the Lagrangian method and see if we can optimize this objective function subject to this given constraint. Now what is the method for Lagrangian optimization? The Lagrangian method starts with this format. So we have a Lagrangian function and we represent that as capital L. At least here there are different notations followed in different books, but today we are going to follow this method. So let me represent the Lagrangian function as capital L. How do we format the Lagrangian function? How do we create this Lagrangian function? We essentially artificially create another function, a new objective function which we'll be using. So what we are going to do is, initially we would usually solve for a particular variable from this constraint, and we would insert it back into the objective function, and hence look at the objective function, the new objective function. So like the previous sum that we did, we would have to optimize this function. This was our original function, this was our original objective function. We transform the constraint, put it into our new objective function, and then we optimize this new objective function. The Lagrangian is sort of similar concept in the sense that it uses a new objective function, but this is not as direct as we do in this procedure. So how do we convert the constraint into our new Lagrangian? Essentially, we first write the original objective function. So our original objective function is x plus 2y. So we write that down. So let me just write down x plus 2y. This was our original objective function. Now what do we do? Now we incorporate, or we introduce another new constant. We introduce a constant. This is not a variable, this is a constant by the term lambda. So this lambda is called the Lagrangian constant. So let me just write that down. This is called the Lagrangian constant. Lagrangian constant. This is a constant. Please note, this is not a variable, so it does not need to be found out the variable value of. So in certain cases you might need to find out the value of this value of this constant, but it's not a variable, it's just a constant. It's a Lagrangian constant, and we use this constant to incorporate our constraint into the Lagrangian expression or the Lagrangian function. So now that we have introduced this lambda, we introduce this expression into our Lagrangian original new objective function. So this is the function that we'll be introducing. How do we introduce that? We think of it as this way. So we write xy plus y square, xy plus y square minus 1 minus 0. So essentially what we do is, we think of it in the implicit function. Had we received the function as xy plus y square equal to 1, this constraint is the same as this constraint, right? This constraint is the same as this constraint. What would we have done? We would have made the implicit form, and we would have taken 1 on this side, and we would have kept 0 on this side. So essentially your job is to convert this constraint into its implicit function and write the implicit form here, so that you have a 0 on this side, and that is what we do here. Essentially minus 0 makes no sense, so you can just simply remove this minus 0 from here, and this is the final expression that you get. Now this becomes your new objective function, and what you need to do is, you need to optimize this. However, there's a catch here. Initially you would have differentiated it with respect to x and y only, and you would have equated it to 0. That was the optimization principle that we usually follow. Here, of course, we are going to do that as well. So we are going to have dl of dx. I am using partial differentiation. Since there are two variables, I would like to keep the other variable constant when I differentiate with respect to one variable. So if I differentiate the Lagrangian expression with respect to x, I'm going to get 1 from the first bracket, and I'm going to get lambda y, because there is an x here, so I'm going to get lambda y from the second bracket, and I'm going to equate it with 0. So that will be my first equation. The next will be when I partially differentiate the Lagrangian expression with respect to y. So that's going to give me 2 from the first bracket. And from the second bracket, I'm going to have, since I'm differentiating with respect to y, I'm going to get a lambda x from here. So I'm going to get a lambda x. That's what I'm going to write down. And then I'm going to get 2 lambda y. So I'm going to write down 2 lambda y from here. So I have 2 lambda y. Again, as per basic optimization principle, I'm going to equate it with the 0, and I get my second equation. Here's the catch, and it's different from the usual optimization principle that we follow. The next thing, there's another equation that we need. Why do we need another equation? Because there are actually 3, not variables as such, because x is a variable, y is a variable, and I've introduced artificially a Lagrangian constant lambda. So I cannot just ignore lambda, right? I have to keep in mind that there's another number over here. So I'm going to differentiate the Lagrangian again with respect to lambda. So I'm going to do dl d lambda. If I do dl d lambda, it essentially gives me the constraint back. So it's xy plus y square minus 1. So it's xy plus y square minus 1. this is the fun of the Lagrangian method. What happens is you essentially end up doing the same thing that you would have done. So these two would have been my original two equations that I would have to solve, and the third equation, this third equation actually gives you the constraint. So this constraint essentially is the implicit function, which is why I asked you to keep the implicit form in this bracket, which is in the product form with the Lagrangian constant. It gives you the implicit form of the constraint that you had. Now what we need to do is we need to solve these three equations and find out the value of x and y. So what we can do is, let me just get another color. So I take the blue color. From here I can write y. So what I'm going to do is I'm going to take 1 on this side. Okay, let me solve for lambda. So I'm going to take 1 on the other side. So I'm going to keep y over here is equal to minus 1 by lambda would have been here. So I'm going to put lambda over here. I skipped a couple of steps. So either we would have y equal to minus 1 by lambda, or I could have lambda equal to 1 by lambda equal to minus 1 by y. I think I'm going to end up using this format more. So I've just kept the two things that I can derive from here. From 2 I will get okay, so what I can do is I can put the value of lambda from the first equation. So I'm going to put the value of lambda from the first equation. I end up with 2 plus, so I'm going to end up with 2 plus, in place of lambda let me put 1 by y. So I will get it as minus x by y, because there's a minus in place in lambda's value, and y is in the denominator, plus 2, in place of lambda I again put minus y. So I get y and there's a minus by y equal to 0. This is from the second equation. That is what I get from the second equation. Now what do I get if I simplify it? Y and y can get cancelled, so I can write 2 minus x by y. Let me bring that minus out. Y and y can get cancelled, so I end up with 2, and this is equal to 0. No, so this 2 and this 2 can get cancelled, and I end up with x equal to 0, because it essentially becomes minus x by y equal to 0, which boils down to x equal to 0. So I get from the first equation I get lambda equal to minus 1 by y, and from the second equation I get x equal to 0. Now let's look at the third equation. So I am going to put this x equal to 0 in the third equation. So since x equal to 0, the first term vanishes, so I get 0 plus lambda square minus 1 equal to 0. So I have y equal to plus minus 1. So essentially my answer is, the optimization is x equal to 0, y equal to plus minus 1. Now what you can then do is you can put the value of x and y in the function and see whether it optimizes. Use the second differentiation to find out whether it's an optimization in terms of minimization or maximization in the second degree. So you just find out the second degree values and check for the second order condition. This is the first order condition, and basically this is the format that is followed when you use the Lagrangian method of optimization.